Hello everyone, welcome to our group presentation for machine learning assignment. Our team consists of 4 members. We tackled one of the most critical challenges in the financial sector today, credit card fraud detection. As digital transactions continue to scale globally, fraud activities are becoming more sophisticated. Financial institutions need automated, highly accurate system to catch these fraud transactions in real time without blocking legitimate customers. To solve this, we formulated the problem as a supervised learning binary classification task using a real-world dataset from Kaggle. However, we immediately ran into the biggest problem in fraud detection: severe class imbalance in our dataset. Fraud transactions represent only about 0.17 of the total records. Because of this, traditional accuracy is misleading metric. To handle this, our group established a shared pre-processing pipeline using SMOTE to balance our training data, and we shifted our evaluation focus to metrics like F1 score, average precision, and ROC AUC. We explored the spectrum of models ranging from simple to highly complex ensemble methods. Specifically, we implemented logistic regression, a decision tree, a random forest, and the XGBoost. To kick things off, I will be presenting XGBoost look at the where that detective made mistakes. The second detective then focuses entirely on fixing the first detective's mistakes, and the third focuses on the second's. It uses gradient descent to minimize these errors over time. By the end, you have a strong unified model made up of hundreds of weak models, perfectly tuned to catch the tricky nonlinear patterns that fraudsters use. To actually implement this, I had to be strategic. To tackle the class imbalance, uh, I used the SMOTE augmented training data, but I went step further. I utilized XGBoot's native scale post weight parameter, setting it to 577.3. This heavily penalizes the model wherever it misses the fraud transaction. Next, I use randomized search CV with 5-fold cross validation to find the optimal hyperparameters. My best configurations used 300 estimators, a maximum depth of 9, and a learning rate of 0.2. I also used the history method, which dramatically speed up the training process without sacrificing accuracy. Moving on to the evaluation, because accuracy is misleading, I focused on the F1 score and the average precision, which measure the true balance between the catching fraud and minimizing false alarms. The XGBoost model achieved the excellent average precision of 0.866 and F1 score of 0.7319 on the unseen test set, alongside an overall ROC AUC of 0.9628. Looking at the confusion matrix, out of tens of thousands of transactions, it only missed 12 fraudulent ones, while keeping false positives remarkably low, just 51. Because of its speed and its handling of complex data patterns and its high F1 score, XGBoost proved to be an incredibly strong model for this task. I will now pass it over to my teammate to present our next algorithm in our study. Thank you.
In this part, I implemented a decision tree model for credit card fraud detection. Initially, the model completely failed, with ROC AUC around 0.5 and F1 score 0. It means it couldn't detect fraud at all. So I improved the pipeline step by step to handle class imbalance, optimize parameters, and improve detection performance. Here I imported required libraries for modeling. SMOTE for handling imbalance, and evaluation metrics such as ROC, AUC, and F2 square. This section loads the dataset and prepare features and labels. One major issue in this original version was improper train test split. So I fixed it by using stratified splitting, ensuring both training and testing datasets contain proportional number of fraud causes. This is critical because fraud data is extremely imbalanced. Since fraud causes are very rare, I used SMOTE to balance the dataset. Importantly, it is applied only to the training dataset, not the test data, to avoid data leakage. This helps the model learn fraud pattern better without artificially inflating performance. Here I trained a decision tree using grid search CV to find the best parameters. Instead of accuracy, I used ROC AUC scoring, which is more suitable for imbalance problem. I also used stratified k-fold cross-validation to maintain the class distribution across folds. Parameters like match depth and minimum sample per leaf help control overfitting. By default, model use 0.5 threshold to classify fraud, but that's not a ideal here. Missing a fraud is much more costly than false alarm. So I optimize the threshold using F2 square, which gives more importance to recall. This allows the model to catch more fraud causes, even if it slightly increase false positives. Here we evaluate the model using multiple metrics. ROC, AUC and average precision shows overall performance, while F1 and F2 focus on fraud detection. F2 score is especially important because it prioritizes catching fraud. This visualization helps interpret performance. The confusion metrics show how many fraud causes were correctly detected versus missed. The ROC curve shows how well the model separates fraud from legitimate transaction. Here is simplified visualization of the decision tree. It shows how the model makes decision based on the feature threshold. This chart clearly shows the most important feature used by the model to detect fraud. It helps us understand which variables influence decision the most. Finally, I added a cost analysis section. Missing fraud has a high cost, while false alarm have a smaller cost. This helps choose the best threshold based on the real world business impact. In summary, the improved model significantly outperforms the original by fixing data, splitting, handling imbalance, tuning parameters, and optimizing threshold. As a result, it successfully detects fraud causes with high accuracy and recall.
Hello, I'm Bhavan Randunu. I'm designing a logistic regression model for credit card fraud detection. In here, first of all, we must import all the necessary libraries for data handling. for evaluation and the machine learning, implement machine learning model and the data balancing techniques. After that, we must import the dataset. In here, we choose the Kaggle dataset that we have found on the Kaggle. In the dataset, we have European credit card dataset of 2013. After that, we must copy into the relevant directory. Then we must check if the data is correctly downloaded. Yeah, these are the first five rows of the dataset. Then we must check if there is any missing values in this dataset. In here, zero missing values in all the rows. Going to data preprocessing. In here, our x and y variables have different variances. In that occasions, the low variance variable get ignored by model. To escape that, we are going to transfer this data into minus 1 into 1 over this range for both x and y variables. So we can ignore that error. After that, we are going to visualize our raw data set. When visualizing, we can detect a huge imbalance in data set. Then after that, we are going to split our data set. When splitting, we have split our data set into test data and the train data. In here, 0.2 mean we get 20% of the data for the test data and the 80% of the data for the training data. Because of imbalance of the data set, we must balance the data set. For that, we have used three techniques and find what is the most appropriate one. First one is random under sampling. In here, we remove the majority classes data set randomly to the minority class, and this means we add synthetic data set to the minority class that level up to the majority class, and the other technique is adaptive synthetic sampler. This is also like SMOTE, but in here we are more focusing to generate minority instances that are harder to learn. When we use these data balancing techniques, we get the balanced data like that. We use this data for training data sets. We have initialized our logistic regression models from logistic regression library. In here, we use two parameters: class weight as balanced and the max ITR as 1000. We have initialized four models according to the four data sets. That means the row one and the rust balanced one, smooth balanced one, and the addition balanced one. And we train all these four data sets. After training, we got the matrix for each models. Evaluation matrix. As evaluation matrix, we get the training accuracy of each, testing accuracy of each, and the precision value, recall value, and F1 score of the each model. This is for original imbalance data set, and this is for RAS model, this is for smart model, and this is for addition model. According to this, we get high accuracy in the smart model. This is the ROC curve. It has highest value for us. If the rust has the highest value, it is not the best method to data balance because it deletes some data. This is credit card from detection model, and it must not delete the data. And the sort is the most most appropriate balancing techniques. And after generating some synthetic data, it maintains 92% recall, and it's significantly good. And as the end of my model training, I have seen that sort is the most appropriate way to set the balanced data in unbalanced raw data set. But in this problem, we must use other assembly method like random forest or SGBoot than the linear model, and we get the more efficiency and more appropriate predictions.
Hi, I'm Navaratna. I implement the random forest classifier for our credit card fraud detection project. Uh, Random forest builds hundreds of decision trees, each trained on a random sample of the data. At every split, only a random subset of features is considered. This decorrelates the trees. The final prediction is a majority vote across all the trees, so individual errors cancel out. Uh, I chose it because it naturally handles our 0.17% fraud imbalance using the class weight equal balanced parameter. No manual resampling needed at the model level. Uh, these are the imports we have done before we start the model training. Uh, we used the Kaggle card fraud dataset, which has 284,807 transactions. which has 30 features. After our shared pre-processing standard scaler, 80/20 stratified split and smart on the training set only. My training data had 454,902 rows, and the test set had 56,962 rows. I trained with 100 trees, max depth 10, square root feature per split, and balanced class weights. Uh, the OOB score, which is out of batch score, a built-in free cost validation came out at 0.9902, confirming the model generalizes well before even touching the test set. Uh, on the test set, which keeps the real-world imbalance, the model caught 84 out of 98 fraud cases. That's 86% recall with 123 false alarms on the legitimate transaction. And the ROC AUC was 0.9810, near perfect ranking ability, and average precision was 0.7933, far above the 0.0017, and noise skill baseline. This is the key metric for imbalance data, and F1 score was just 0.5508. The precision is low at 0.41 because of false alarms, but recall at 86% is what matters in fraud. Missing a fraud is far more costly than a false alarm. Features importance showed V14 as the strongest fraud signal at 0.24, followed by V10, V4, V17, and V12. And the limitations and improvements are the two main limitations is it's a black box with 100 keys, hard to explain to regulators, and it's slower to train than logistic regression. To improve it, lower the classification threshold from 0.5 to around 0.3 to boost recall, switch to XGBoost for better precision recall performance, and add SHAP values for explainability. And that's my section. Thank you.